So, section 1.5. Okay, the purpose of this section is to introduce a concept called region and or subdomains, or we might unofficially call them subdomains, or boundary regions. You could define finite domain spaces just on a region, on a part of the domain. You could integrate only on a region, on a part of the boundary, for example. Okay, so to sort of encompass all of these, NGSolve has an object called region. Okay, we'll see what region is all about. Okay, first, whenever we construct a geometry, we would like to give some names. Like when we make a rectangle, we would say that its boundary parts may be bottom, right, top, left, or just B, R, T, L. So you can decide your own names, and those will be the names that are stored in the geometry. This is the geometry object. Right? So in this example, we constructed two rectangles, one smaller than the other. Okay. So if you go here and you look at the geometry, you see two rectangles, right? The outer one and the inner one. We call the outer one outer and the inner one inner, and you see how you can give names to the materials. We could think of this as one material and this as another material. That's why you have the command sit material. But in this tutorial, we're going to think of these as region objects. Okay, and you can look at the mesh, and you can double-click on one of these, and then you'll see even through the mesh that you have a separate subdomain. Okay, now, you're free to define a finite domain space on just a subdomain. And the way to do it is, this is the same old Lagrange space. It's a mesh. The new thing is this defined on flag or keyword. When you say that this finite domain space should be defined only on the inner subdomain, then the functions are essentially, we should think of these grid functions of these finite domain spaces essentially supported on that subdomain and nowhere else. So when you plot it, here's an example. This is a function that is defined here, nowhere else. If you ask for the value of this grid function outside, bad things will happen. Okay. Yeah. Undefined. Okay, right. Now, so you might think that this finite domain space, since it's only defined here, should have less degrees of freedom, and yes, it should have less degrees of freedom, but that's not reflected when you type end of, the total number of degrees of freedom. A mesh that is defined only on the inner subdomain, and a mesh that's defined, a finite domain space that's defined only on the inner subdomain, and a finite domain space defined everywhere, would have, when you print out, it says it has the same degrees of freedom, but again, the confusion is resolved if you look at the types of the degrees of freedom. And this time, what you have to look at are the freed-offs. You look at what are the free degrees of freedom that participates in the solution for this finite domain space defined only on the inner region. And you see that almost everything is zero here. So these 4 degrees of freedom are participating, these are participating, these are participating. Everything else is zero. Okay, you can also look at the coupling degrees of freedom. And in the coupling type of the degrees of freedom, you see another new object that you didn't see in the previous case called unused degrees of freedom. These are the degrees of freedom for this space on the subdomains that are not used. Okay, so when you make a vector and do linear algebra with vectors corresponding to grid functions on this function spaces on subdomains, you just want to use memory for exactly what the number of degrees of freedom inside this subdomain, not for the rest. And the way to do that is a new command called compress. You take the finite domain space, which is defined only on a subdomain, and you call compress. You get a compressed a degree of freedom which only has space to allocate, which only whose grid functions have only space to allocate vectors here. Right, so you're not wasting any degrees of freedom. Okay, some of the things you can do with region objects. Okay, here, integrate on regions. Here's an example. You have a linear form. Okay, I thought I had another example somewhere here, but okay. So, but okay, let's proceed along and see what happens. Here's a linear form, and this linear form involves only integration on the inner subdomain, plus an integration on a boundary region, and this is the top region of the mesh. Okay, so you saw the dx before. Now look at this ds. ds is also a differential symbol, but it represents integration on the boundary. Okay, and you can restrict that integration on the boundary to a single part of the boundary by calling defined on equals on whatever region you like. Right, so in this case, it's just the top region. We're just integrating v over 10 on the top region. So this integral is represented by this. This integral on the inner subdomain is represented by this. Okay. You can give flags to ds and dx, and you can look at. You can ask for more information. One thing I do want to point out here, if you look on the online help, on the doc string for dx, then you see that in the call method, the defined on takes as argument something that looks like this. Okay, so that means what you provide here in the defined on argument, it could either be a region object. A region object is what we just created here, or it could be just a string. Right? That's what it. That's okay. If you read it carefully, you see it's an optional argument which either takes a value that's a region object or takes a value string. Okay. So what I did here, I could equally well have defined using this. Right, this might be shorter. You just give it a string and say, okay, just integrate on the inner domain. It'll translate that to a region inside the code. Okay. Okay, so we can solve a problem. Here's some sort of, I don't know what this is. Some heat generation here, some heat generation at the top, and here's a steady state heat distribution. Okay, what more can we do with region objects? You can do more things than just here. You were able to give a string that then got converted into a region object. But if you have two region objects, you can do more things than just strings. You could add them. You could take the complement of it and so forth. So let me show you some of it here. Here you have the two subdomains, outer and inner. You have all the boundary regions here, B, R, T, corresponding to the big rectangle and the small rectangle. Okay, if looking at mesh.materials with the inner tells you that this is a region object. This is how you know the type of, and you see that the boundaries are also region objects. They are the same type. Both of them are the same type. And you can do operations with regions like this. For example, if you look at mesh.materials and you ask for its mask, the mask gives you two numbers, 0 or 1. The first one is 0, indicating false. And the second, there are only two subdomains, so corresponding to two subdomains, there are two numbers. And when the number corresponding to inner is given the value 1. So this is how the mask object tells you what is the region. So now you can put in a regular expression and say, well, look at all possible regions and give me its mask. And in this case, there are only 2 regions, so all regions are marked by 1 or true. You could ask for boundaries and mark only the top or the left boundary, and you see that the top boundary and the left boundary are marked 1, and everything else is 0. You can add regions. Suppose you want to add the inner and the outer subdomains to get the whole domain, and to verify that whether you've gotten the whole the whole region, you print out the mask and you see both regions are true. You can take the complement. Right, the complement is this. That little thing is taking the complement. You can subtract. You can set piecewise coefficient functions. For example, here's an example where you set up a coefficient function that is 3.7 on the inner subdomain and 1 on the outer subdomain. And here is a Pythonic technique for not caring about the ordering. Mesh.getMaterials gives you the subdomains in some order that's internal to NGSolve, and you don't want to care about it, so you declare it in a readable way, and then you convert it into a list in the same order that NGSolve expects it, and then you give a list of values to the coefficient function. This is another way to initialize a coefficient function. You give a list of values corresponding 1 for each subdomain, and it produces a piecewise constant function. All right, and this might be a little bit complex topic if you're not used to it. So there are some extra exercises with lots of pitfalls and so forth. So I leave you to work through this as bedtime reading, and I'll proceed to the next tutorial unless there are questions.